Hello, everyone. Welcome, welcome. I am excited to introduce our next speaker today. We have Meltem Ballam, and she is the Data Scientist Fellow at General Motors. And her talk today is entitled Backbone of Computer Vision Pipelines, Feature Extraction. Please welcome Meltem to our virtual stage. Meltem, you can come on up. Okay, great. So I'm going to turn my camera off and you can start sharing your slides and take it away. Hold on, we can't hear you, Meltem. Is your mic on?
My mic is on.
There we
And
go. Okay, we can hear you.
awesome. Screen sharing had a little bit of a glitch. Sorry about that. But since we are going to talk about technology today, we can forgive that. So hi, everybody. This is Meltem Ballam. I work for General Motors as a data science fellow. But before I joined GM, I spent 2 decades working on computer vision and image processing problems, both as an engineer and a computational neuroscientist. First of all, I would like to thank organizers for the invitation and welcome you to my home office. The most important part of computer vision is feature extraction. Vast majority of algorithms are developed around extracting best representative features of objects. Today, I will deep dive into those features and the feature extraction techniques. Let's start with outlining today's talk. I'll give an intro to image processing. I'll give you a little bit about history, the story behind the most referred image in the discipline, most common image formats, and definition on an image in details. My goal is to show you the human perspective and also computer's perspective of the image. So I will touch base to some techniques used in physics, visual cortex studies, and psychology. Later, I will provide some common tools depending on your background and where you are at in your career. I will then touch base to thresholding and morphology. The hope is to leave you with a laundry list of items involved in computer vision so that I'm leaving you with a bonus part of my talk that you can see the full cycle of a computer vision project and you can implement it by yourself. All in all, I wanted to show you what has been done in the field and the future of possible, the art of possible. Oh, this is not a trick slide, but rather important one. Today's topic is the objects, and objects are also the data. There are 4 universal rules in data. Data is never clean. You will need to clean your data first. The simplest solutions are always the best solutions. Big data is just a tool, not an answer to data. So let's see how far we can go today with our particular data, images, and feature extraction. Let's begin with the introduction. I believe that past is the reflection of the future, and it is no different in the computer vision. Technology is constantly affecting the change in the computer vision while evolving within. Second World War was one of the biggest triggers moving technology forward. For example, JPL, MIT, and Bell laboratories were developing communication and internet technologies for military, and eventually it became available for us to use in 1970s. Real-time information processing became possible in 1975, and we were able to watch color TV. 2000s were the years that we met the fast computers, and computers computers became part of our lives. We started to playing computer games. Last several years, cloud became available for everybody, and IoT became part of our daily lives. We all use Instagrams, we all use Facebook, everything all together. We have a lot of images shared, digital images shared on those platforms. But before, since we are talking about computer vision, we have to definitely talk about Lena. Lena is a symbol of an era. There are goods and bads between the lines of this image. The picture was taken by a Playboy photographer and published in the magazine in 1960. Later, it became the most iconic picture in the computer vision. Computer scientists, neuroscientists, psychologists, psychiatrists has been using this image since 1973. The significances were that it was a human face and glossy with a lot of contrast and lines. Since then, it has been used as the standard test image for computer vision, biologically motivated image processing like retina studies, and robot vision. She revealed the story of the image, of this particular image that she's holding here in 1997 at the 15th annual conference of Society of Image Science and Technology. Admittedly, I didn't know the story until then. When we talk about attractive women in computer vision and image processing, it is also worth to remember Kodak Shirleys. Not too surprising, one of the Shirleys was again Lena. Throughout my career, I had mixed feelings. Most definitely, she's the most used when it comes to image processing and colors. And I used this image over and over throughout my 2 decades career. It has been only the last 10 years the gender bias has been discussed around this picture. Once again, Lena is front and center. I definitely learned from her picture over the course of my career. The contour and flat edges represent how we process and identify objects and then name it. I definitely felt lonely in the engineering classes and had questions about this picture. I'm also an advocate for growing women in data science and STEM, but again, Lena wrote a history and led computer science to the point we're at. I will use Lena in this talk in the following slides. It is again up to you to decide how you will test and implement your algorithms, and I definitely suggest you to go see the documentary about this. I want to start with the basics of image. The definition of an image we will discuss today is a picture that has been taken, scanned, or copied and stored in databases or in the cloud. There are 4 main formats that I want to include here. First of all, JPEGs. They are stored in 16 million colors. The combination of colors are produced by using 8 bits each color in red, green, and blue. The compression is 10 times more powerful than bitmap to store images without degradation. However, high compression rate might cause noticeable noise and quality issues in the image. GIF format is better to store images with text. GIF uses lossless compression that does not degrade the quality of an image. However, GIFs can only store images of 256 colors. GIF supports animations by storing a stream of images in a single line. PNG can be described as the more developed version of the GIF. The PNG format supports 24-bit colors, same as JPEG format. Therefore, PNG image may include over 16 million colors. TIFF supports up to 24-bit colors. The compression can be chosen as lossy and lossless depending on the user's needs. So it is important to know the format of an image to gauge what the limits and needs are. However, the resolution of an image is essential to start your analysis. The resolution is defined by dot per image. In printing, DPI refers to the output resolution. Computers don't have dots. However, they can analyze the images with pixels. Pixels per inch is the terminology used and refers to the input resolution of a photograph or image in computer vision. So nowadays we use DPI and PPI interchangeably. You can always check and see the DPI and PPI of your image and also adjust it to your needs as the first step of feature extraction. I will be silent for a sec for you to check and see how you can actually check the DPI and PPI and change the DPI. And again, I used Python here. The basic library PIL is used here. So let's begin with the digital image. Images can be a picture with a background text, a picture taken from an accident, money transcripts, animal pictures, nature pictures, scanner, and printer outputs, everything and anything that you can see with your eyes and process it. But when those are entered in the computers, they become just numbers between 0 and 255 as shown here. You heard me using image, computer vision, and patterns up until now. Before I deep dive further, I want to clarify where I stand. When it comes to image processing, computer vision, and pattern recognition, these terms are all together. In your career, you will see a lot of these words coming together, and it has been used interchangeably between the disciplines. The closest disciplines to computer visions I can see are image processing and pattern recognition. I strongly believe that these terms are lined up together and the differentiators are very slim, if none. You will hear and see slides like this throughout my talk, as I want to provide a whole picture within 25 minutes. The ultimate goal is to represent the objects as human can see. So we computer scientists or wannabes implement physics and psychology behind image processing. If nothing else, we use it to start conversation at a cocktail party. So let me tell you a little bit about fractals and illusions. I hope that you can actually start implementing these techniques. The images with repeating patterns and features are called fractal images. Two basic questions we ask to identify if an image is fractal or non-fractal. One, is there a new feature revealed when we put the image under a magnifying glass? Are there different sizes and scales of the same image? The leaves, the freckles on apricots, and even the worm bites on the leaves are the fractals. I'll try to explain the theory as Larry taught during my PhD, but it is a complex topic and it will take me more than 25 minutes to explain in details. I definitely suggest his book if you want to learn more about the fractals. The technique is used to compress images, or in our case, for the feature extraction. Even though some of the features are lost during compression, fractal code can be used to recreate an image or extract the features. There are three main properties to remember. One is the self-similarity, and the second one is scaling, and the last one is dimension. As it is shown in the picture, the image or the feature in the image can be enlarged by a window until the wiggles resolved. Scaling provides the ratio of biggest and smallest spatial resolution. In other words, scaling basically reveals the number of divisions. Dimension provides the number of new features at the highest magnitudes. In other words, number of smallest shapes are called dimension. Hope this will give you some starting points so you can employ fractal coding for your AI algorithms in the future. Oh, before I forgot, try quad tree decomposition or Huffman decomposition for an image that I showed here. Illusion is one of the terms which is borrowed from different health sciences, psychology, vision, ophthalmology. Hope that illusion will lead to the basic features on an image and geometry of the pieces of an image. Here I will limit my topics with the Shepard's table illusion, checker illusion, and Amos Room illusion. Let me start with the Shepard table illusion. One of the most used concepts is this particular picture here. In Shepard's study, one table seems longer and thinner than the other one, even though it is actually identical to the other. The receding edges of the tables are seen as if stretched in depth. The table which looks like square is further away and appear wider. This tells us the power of depth in an image and how to represent in the computer. This is an example of the checker shadow illusion, and it was first represented in 2005. The green object is obviously shadowing the checkerboard object. The optical illusion of the shadows makes the upper left corner of the image darker. However, in reality, checkerboard has identical brightness for both gray and white squares. If you were to print, the entire board will look identical. The last one and most exciting one is called Amos Room. Don't you think that the man on the right is giant? Is in fact the angle that you're looking at, and the giant man is much closer than others to trick your eyes. The room is actually almost a triangle. The person on the right corner is the closest to your eyes. Isn't it amazing? So these algorithms and the mathematical models have been developed since 1800. However, they are the victims of not having enough data, lacking the storage, and lacking the computation power. So, I was almost forgetting power of the open source tools in this slide. So let me start with some of the open source tools that you can actually implement. So one of the tools, if you're coming from academia like me and familiar with MATLAB, Octave is one of the tools that you want to start with. It is very powerful because it was developed for the numerical computation. And images that we're talking, as I showed, it's between 1 and 255. So this tool is one of the best tools that you can start with. So this is a starter slide that you can go download Octave and start using some smoothing algorithms, and then end up seeing this little friendly face here. So the other tool that you can actually use is Rstudio. R is a statistical tool that has been widely used, and I'm sure you heard about that. And they also have a lot, R also has a lot of image processing libraries for you to choose. My favorite is Python. Unlike R and Octave, Python is widely used general programming language. There are a lot of different IDEs and libraries to use in Python. One of my favorite here is CV2, so you can go start your algorithms there as well. And when it comes to my projects, I leverage tesseract for text extraction from images and opencv for image processing. Both are widely supported and have extensive help. You will see some examples in the bonus material for that. As I promised, we're getting back into Lena and most used techniques in the field. There are three main steps to deal with an image. First, clean the image, then start dicing into detail that we can use in the future for robot vision or AI. And I will start with thresholding. It is the simplest way of separating the background from foreground. So first thing we do is to separate background from foreground and then reduce the colors. So it is called grayscaling. So we simply represent the image in grayscale to begin with. This will reduce the algorithm cost. And yes, even with today's technologies, this is important to reduce algorithm cost. So we actually reduce the colors between black and white using a grayscaling technique. And thresholding is basically changing the color schema with a threshold value. And let me give you a couple of examples as we have about 3 minutes here. The most common algorithm is global thresholding. It's the most basic implementation of that. And everything else has been built like histogram, local thresholding, OTC thresholding, clipping, gradient-based thresholding. They are all built around that. And the last slide that I wanted to share is morphology, which actually you extract and compress your lines, and it is mainly used in the medical technologies or in the text reduction. And then I want to share dilation and erosion here, but I'm going to share these slides for you to share, for you to use and learn more in the future. And I put some extra transformation techniques, and then you will see a bonus part. But again, before I finish my talk, I would like to thank you for joining me today, and I would like to keep conversation either by email or in my social media channels. Thank you very much.
Great. Thank you so much, Meltem. Everyone, please give her another warm virtual round of applause, and we'll see you in the next session.
Thank you.